In this video, you are going to learn how derivatives affect the shape of a graph. So first thing is the increasing decreasing test. If the derivative is greater than 0 on an interval, then the original function is increasing. So if this was a function of the derivative, therefore anywhere it is above 0, so anywhere it is positive, which is going to be from here to here, it is positive, and from here to here, it is positive. That is where the original graph will be increasing. So from this point to this point, which is about me right here to here, it is going in between that interval, it is going to be increasing some way. We don't know where, we just know that it is going to be increasing. And then at this point, so somewhere on here, it is also going to be increasing. And then again, if anything is less than 0, if anything is less than 0, which would be everything below the graph of the derivative, then the original function would be decreasing. So up to this point, it actually is going to be decreasing, increasing here, from these two intervals, decreasing again, and then increasing. So it's going to look relatively something like it's going to go down and then up, and then down, and then up. That is the increasing, decreasing test. Now to do it algebraically, what you'll do is the first thing you're going to do is you're going to take the derivative. So that will be 12x to the third minus 12x squared minus 24x, and the derivative of 5 is just 0. And now you're going to set it equal to 0. So I'm going to factor everything out that I can. Well, they all have a 12 in common and they all have an x in common. And when I factor out a 12x, I am left with x squared minus x minus 2. And now I'm going to set them equal to 0. I will have 12x equal to 0, which means divide by 12, and I'll get 0. And then I'll have x squared minus x minus 2 equals 0. And this actually factors into two parentheses, x minus 2 and x plus 1. And so then I will set them individually equal to 0. And so my zeros are going to be 2 and negative 1. And so these are all three of my zeros. Now I am going to create a number line. So I'll have 0, I'll have a 2, and I'll have a negative 1. And I'm going to choose numbers on all different sides, and I'm going to plug it back in to my derivative. Plug back in to derivative. And you're wanting to know if it's going to be negative or positive. It doesn't matter what the number is. You are only concerned about negatives and positives. So if I think of it as in terms of 12x, x minus 2, and x plus 1, I can plug in numbers. So I'm going to choose negative 2. So if I try with negative 2, this will be negative. Negative 2 minus 2 is negative. Negative 2 plus 1 is also negative. 3 negatives will give me a negative number. Now I'm going to choose a number. I'm going to choose a negative 1/2. So I'm going to do this again. So with negative 1/2, I will get a negative here. Negative 1/2 minus 2 is a negative, but negative 1/2 plus 1 turns positive. All right, I only have two negatives. Negative times a negative actually turns to a positive. And now I'm going to do it again with the number between 0 and 2. So I'm going to choose a 1. So if I plug in 1, 12 times 1 is a positive. 1 minus 2 is a negative. And 1 plus 1 is a positive 2. I only have one negative, so my answer is going to be negative. And then I'm going to plug in a number on the other side, which is going to be, in this case, a 3. And so 12 times 3 is a positive number. 3 minus 2 is a positive 1, and 3 plus 1 is a positive 4. So you have all positive numbers. So we're wanting to know, where is it increasing, where is it decreasing? So it is going to be increasing, obviously, where the derivative is positive, and then of course it is going to be decreasing where the derivative is going to be negative. So my increasing intervals will be from -1 to 0, and then from 2 to infinity. Decreasing, where I'm looking for my negatives, is going to be from -infinity to -1, and then from 0 to 2. And that would be my answer algebraically. Now there is actually two tests that we're going to discuss. The first derivatives test and the second derivatives test. In the first derivatives test, you're going to be able to determine local min and maxes from not just a graph, but also from doing it algebraically. So the first one, a local max is going to happen if the sign changes from a positive to a negative, meaning like up here in the signs, we had a positive and then we went to a negative. That is going to determine a local max. A local minimum is when the sign is going to change from a negative to a positive. So we actually can look back up here and determine what is a min and max. So you went from a positive to a negative. So I know that this is actually going to be a maximum at this point at x equals 0. I also know that it went from a negative to a positive here, from a negative to a positive. And so I know that x equals 2 will become a minimum. We don't know if it's the absolute minimum or if it's just a local min, but we do know that since it went from negative to positive, it would be a local minimum. So here are some graphs to show this is a max because we went from increasing to decreasing, positive to negative. Here we went from decreasing, the function decreased and then it increased. That means the derivative was negative and then positive. Now here is where you don't have a max or a min. Something is going to happen possibly when you do the algebra of it, but the sign doesn't change. If you notice here, it goes from a positive, increasing, and it's still increasing. It hovers, giving you a tangent line of 0. It's a horizontal line, but the sign does not change. So what that would look like algebraically is if I had some numbers, like let's say 4, and then we had numbers on the side, and let's say that when we did the sign test, it was a positive on this side, but when we did it on the other side, it actually was also still positive. When the sign does not change, that is where something like this is going to happen, to where you're going to have a horizontal line, but it does not change signs. So for practice, at what value does the original function, okay, be careful. This is a graph of the derivative. So we're looking at positive and negative. So we're looking for when it's a local max or min. So this is going to happen here and here. Remember derivative. It's negative here, it's positive up here, and it's negative here. So if you think of it as a sign change where the derivative equals 0, remember, when the derivative is 0, which was at 1 and at 5, on the left side of 1, it was negative. In between 1 and 5, it was positive. And after 5, it was below the x-axis, and so it's going to be negative. So we're looking for max and min. So I see that it went from a negative to a positive right here. That is automatically going to be a minimum. And then from a positive to a negative, that is a max. So we can say that there was a local max when x equals 5, and there was a local min when x equals 1. Again, remember this is the derivative graph, so we're looking for when it's below the x-axis and above the x-axis. Now let's do it algebraically. We want to find local max and mins for the value. So the first thing we have to do is we're going to have to take the derivative. So the derivative is going to be 12x to the third. Oh, we already did this. 12x squared minus 24x, and then the final one to 0. And we did 0, and we came up with the fact from above that x was 0, that x was 2, and that x was -1. And so the next thing we did was the line test. We had 0, we had 2, we had -1. So there was a negative and then a positive, and then a negative and then a positive. And now we can determine at those points what happened. Was it a local max or min? So from a negative to a positive, that is a minimum. From a positive to a negative, which means you went up and then down, that created a max. And then from down to up, that created a minimum. So therefore, we would say that there was a local minimum at x equals -1 and at x equals 2. There was a local max at x equals 0. So pause the video, you try to do this one on your own, and then resume to see the answer. Okay, for this one, first thing, again, we always have to do is take the derivative. So the derivative of x is 1, and the derivative of 2 sine is 2 cosine. Now we set it equal to 0. So to solve, I'm going to subtract 1 and divide by 2. And so we're looking on the unit circle, where is cosine -1/2? And that is when x is going to be at x is -1/2 at 2 pi over 3 and at 4 pi over 3. Remember, cosine is the x value on the unit circle. So next thing we do is we do the line test. So we have 2 pi over 3 and we have 4 pi over 3. Okay, so we need to come up with numbers on either side. Well, 0 is always a great number to use. And then between 2 pi over 3 and 4 pi over 3 is pi. And on the other side of 4 pi over 3 is 2 pi. So let's start with 0. If I plug in 0, I will get 1 plus 2 cosine of 0, which is going to be a positive number. So it's positive. Okay, so now I'm going to plug in pi. So 1 plus 2 cosine of pi. Cosine of pi is the number -1. So I'll get 1 minus 2. So that's actually going to give me a negative. And now I'm going to plug in 2 pi. 1 plus 2 cosine of 2 pi. 2 pi is the same thing as 0. So I know I'm going to get a positive again. Okay, so now that I have this, I can now determine max and min. So at 2 pi over 3, we went from a positive to a negative, which means we went up and then down, which means that was a max. And then here we went down and to up, which is a minimum. So therefore, we can say that there was a local, max when x equals 2 pi over 3. And then we could say there was a local min when x equals 4 pi over 3. Then there's a second derivative test. This helps you to understand concavity. So these two graphs are both increasing from A to B. However, but they look different because they bend. This is actually considered concave up, because think of it as a smiley face. This is concave down. If you keep going, you would have a frowny face. So we can determine how it is going to curve, meaning at the very beginning, we had this graph, which is pretty accurate when it came in terms of increasing and decreasing. However, we do not know in which way. Like, did it curve like this? Or was it curving like this? You don't know that, which is why we have the second derivative test. And so here's how you actually are able to figure out the definition of what to do. When it's concave up, the tangent lines are actually continually to increase. Like the slope of this line might be like a half, yet the slope of this line is 3. So as you're going from left to right, the slope is actually increasing. Or you could have slopes that are decreasing, like this slope could be like a -1/2, and this slope can be like a -4. It is decreasing. They are getting lower. And then you have concave up, in which the tangent lines are going to increase and the tangent lines are going to decrease. So the test is if the second derivative is positive, it is going to be concave up. If the second derivative is negative, it is going to be concave down. This is called the second derivatives test because you have to use the second derivative to find out the answer. And then you also have something called inflection points. So when you're taking the first derivative and you set it equal to 0, that gives you your max and min. When you take the second derivative and set it equal to 0, it is going to give you the inflection point. The inflection point is where something is going to curve from concave up to concave down, or concave down to concave up. So that is what an inflection point is going to create. So the second derivatives test, okay, if the first derivative is 0 and the second derivative is negative, you're going to have a local max. It's going to be a concave down. If the first derivative is 0, which means there's going to be a max or min, and the second derivative is positive, you automatically know it's going to be a minimum. The reason that is helpful is sometimes you cannot create a line test and do negatives and positives to find if it's a local max or min. So we're going to practice. We have a function. We're going to try to find everything that we can. So the first thing we're going to do is we're going to take the first derivative. Okay. I'm going to go ahead and at this point take the second derivative as well. Okay. This is going to represent concavity. This is going to represent max and min. So let's go ahead. Starting with the first derivative. I'm going to set it equal to 0. So I'm going to set, I'm going to pull out a 4, and I can pull out 2 x's, and I'm left with x minus 3. So I will set them both equal to 0. I'll get x equals 0, and I'll get x equals 3. Okay, I could create a line test to show local max and min, but I'm going to go ahead and actually go over and do the second derivative test. So when I set them both equal to 0, I'll get x equals 0, and I'll get x equals 2. Okay, these are called inflection points. Which means that if I was to graph the original function, I know that at 0 and 2, it is going to turn to become either concave up or concave down. These are what you call local extrema. These are going to represent the local max and min. So we can do a couple of things. One, I do notice that at x equals 0 and x equals 0, there is an inflection point and there's a local extrema. And then let's go ahead and do the line test to figure out all the other stuff. So I have 0 and I have 3. So I'm going to choose numbers. I'm going to choose a -1, a 1, and a 4. So I'm going to plug -1 back into here. So I'll get -1 squared, which turns positive. So let me just rewrite it up here. When I plug in -1, this actually still turns positive because it's squared. And then -1 minus 3 is a negative. A positive times a negative is a positive. Now I'm going to plug in 1. When I plug in 1, I will get a positive still. And then 1 minus 3 is still negative, which means negative. This is where I notice it does not turn. It's decreasing to 0. It flattens out, but then it keeps decreasing. So there is no max or min. No max or min, which means it's just an inflection point like we nosed over here. Now at 3, if 3 squared is still positive, I'm sorry, I got to plug in 4. When I plug in 4, I'll get a positive because it's squared, and then 4 minus 3 is positive, so that actually is. So the only max or min is actually at 3, and you went down and then up, and so it is going to be a minimum. So I know so far that there is a min at x equals 3. Now I'm going to go over and I'm going to find out my concavity. So I have 0 and I have 2. So I'm going to plug in -1, 1, and I'm going to plug in 3. And I'm going to use the 12x times x minus 2. So when I plug in a -1, I'll get a negative times a negative, which is positive. When I plug in a 1, I will get a positive. 1 minus 2 is a negative. Positive times a negative is a negative. And then when I plug in a 3, I'll get a positive times a positive, which is positive. That means it's concave up here, concave down there, and then concave up there. The only other thing that you can do is you can figure out, you know that there's a max at x equals 3, but you also can figure out the actual coordinate point. So to find the coordinate point, plug 3 back into the original function. So if I take my original function and I plug in 3, I will get -27. So I could say that there is a minimum at the point 3, -27. Now, what an inflection is doing, if I was to graph a very, very, very rough sketch, what's happening is that at 3, -27, which is, let's just say it's way down here, there's a minimum, which means I know it's doing that. And I also know that at 0, there is an inflection. Okay, at 0, it was concave up, which means like it looks like this, but then at 0, it turns and becomes concave down. That is how the whole thing is decreasing from all the way over here. That's what the decreasing means. It's going negative and then it keeps going negative. It's because it is still completely going negative, but that's why there's an inflection point. So somewhere here, it is becoming a concave up to a concave down. And then at 2, here it turns and becomes concave up again. That is actually how you can, and we will do this later, of sketching graphs based off of all of that information. So last practice, let's determine which values are represented by the following. The first derivative and the second derivative are both positive. If the first derivative is positive, that means the function is increasing. If the second derivative is positive, that means it's concave up. So where is the graph increasing and concave up? And that should be at B. It is increasing, and you can tell that the curve is concave up. Next, they are both negative. So we are looking for when it's decreasing and concave down. So where is it decreasing and concave down? It's decreasing here to here, and it's decreasing here to here. But we need concave down. This right here is concave up. So that must be E. Next, the derivative is negative, which means it's decreasing. We're looking for decreasing and decreasing. But the second derivative is positive, which means you're looking for concave up. So which one of these is concave up? And it's A.